Hello students, welcome to the class. So today we will do the JPYQs part 2 of the chapter classification of element and periodicity of properties. So this is the disclaimer. Here is your first question. Calcium 2 plus has a smaller ionic radius than potassium plus because it has. Now this is from the year 1993 and it is a subjective type. So we are attempting the subjective type also here so that you can get source of all the type of questions that were previously asked. So sometimes it happens that questions from the subjective type is framed and asked in the objective type in the recent years. So for that thing, I am making this question available for the PYQs part. So you have some time to solve the question. Your time starts now. Just think about the most appropriate reason related to the difference in size. Okay, your time is up. So what will be the answer? It would be high effective nuclear charge. Now why I'm saying it? It must be high effective nuclear charge. For that, we have to look at the electronic structure of these two species. First, these two species are calcium 2 plus and potassium plus. So they both are ions, of course. And the electron count in both of them is same, which is 18 electron. Now, we have read it multiple times in the previous classes also. Whenever you see that isoelectronic species are present, you say that ionic radius is inversely proportional to the integral value of charge. We have seen that. But what is the exact reason behind it? So, since they are having 18 electrons, but the count of proton is completely different for both of them. Potassium plus is having 19 protons and calcium 2 plus is having 20 protons. Therefore, due to this extra proton which is present in case of calcium 2 plus, there will be a higher effective nuclear charge. Means the charge on the center, I would say the positive charge on the center is increased by 1 unit here. And what it does, it strongly pulls the calcium 2 plus inward more strongly as compared to the potassium plus due to the larger number of protons. And that results in the calcium 2 plus ionic radius to get contract. Okay, you can see here it is written that stronger pull reduces the electron cloud size. I hope this is clear to you that why are we saying that you should write high effective nuclear charge as the answer for this. Now moving on to the next question. Now for this question, there is a problem that we don't see the part of it in the NCRT about the Mulliken scale. That how do we calculate the formula or the electronegativity for the on the Mulliken scale. So for that reason, I have put up this question so that you can also see the correct formula. Now those who of you know about the correct answer for this question, they may answer it. But still you can answer this question without knowing this formula. Remember, when we are talking about the electronegativity, there I said that there are three skills that help us to assign values of electronegativity to different elements. It was Pauling scale, Mulliken scale, and Jen Boswell scale. Right? So, of course, your answer would be what? If it is Mulliken scale written here, so what was the physical property that was defined by Mulliken? Okay, your time is up. So, the correct answer will be electronegativity. And what was the formula for the electronegativity? The formula goes like this. So, first of all, according to Mulliken scale, we write that electronegativity chi is equals to ionization energy plus electron affinity by 2. So we simply take the average of these two physical properties. So here I is representing the ionization energy and the EA is representing the electron affinity. Therefore, we can write the final correct statement as on molecular scale, the average value of ionization potential and the electron affinity is known as electronegativity. Moving on to the next question. Again, this is a subjective type, but be careful before answering this question. You may predict it wrongly because two very close terms are being used for the same process. But here it is said that you have to term the physical property which is related to the energy released. Remember, energy released when an electron is added to a neutral gaseous atom. So your time to solve this question starts now. We have already talked about the definition where we say that, okay, the energy released is related to a certain physical property. Your time is up. So just think about it one more time before I move on to the answer. So there is a much more closer term uh, related to the electron gain enthalpy. What was that? Because here we have to consider the energy released and not the energy change. Okay, so let us move to the answer. So the correct answer will be electron affinity. Now, to do this question, 2 points are noteworthy here. First is, if you are talking about the energy released, then energy released is simply equals to the negative of the electron gain enthalpy. And the second thing is, your electron affinity is also equals to the negative of electron gain enthalpy. So both are having the same value. Therefore, what we can say that your energy released during addition of electron to a neutral gaseous atom is called as electron affinity and not electron gain enthalpy. Then moving on to the next question, you have to arrange the following ions in the order of their increasing radii. So 4 ionic species are given here, and this was asked in 1997, and it is also a subjective type. Remember, students, that this all are not isoelectronic species. Okay, so this should be noted here. You can just try to calculate the number of electrons in each of this, and therefore you can't use the general term that your ionic radius is inversely proportional to the nuclear charge on the atom. So your time starts now. Just think about all the possibilities that is regarding your shell and your effective nuclear charge. Both are varying here. So what will be the order for this? Ionic radius order. You have 5 more seconds to solve it. Okay, your time is up. So the correct answer will be, first, the smallest one is the lithium plus. Then comes your aluminium 3 plus, magnesium 2 plus, and lastly your potassium plus. Let us try to understand this trend first of all. So if you see the trend, then 2 points should be remembered which affects the ionic radius. First is the number of shells. So more is the number of shell, more will be the size. And you know, down the group, the number of shell increases. The second point which should be remembered is about the high positive charge on nucleus. But this is only true for isoelectronic species, right? So if they are isoelectronic species, then the one with the greater charge will have the smaller size. Now let us analyze all of these ions and see that what is the number of shell and what is the electron and proton count in the given species. So if you analyze all of this, what you will get? You will get the analysis of ions as for aluminium 3 plus there are 13 protons and 10 electrons because 3 electrons are being removed. So they are having the highest nuclear charge with 10 electrons. Second thing about magnesium 2 plus. So here the number of protons has been changed but the number of electrons is same. But it has a lower nuclear charge as compared to the magnesium 2 plus as compared to the aluminium 3 plus. What about lithium plus? Although it has the least number of protons, but it has only one shell. So that is important to note here that your lithium plus has one electron shell here. If you take the case of positive potassium, then here the number of protons has increased. But what about the shell? The number of shell has also been increased. So 3 shells are present here. Why? Because your potassium falls in a region where there are 3 energy levels possible. The potassium plus. But your magnesium 2 plus and 3 plus are not in accordance with that. I hope you are getting the point, right? So you have to consider both the factor, your shells also and your nuclear charge also. Now we have done the analysis of all the ions. Then we can move on to comparison. So what is the first comparison? That your aluminium 3 plus and magnesium 2 plus are isoelectronic. And since they are isoelectronic, what we can say that your aluminium 3 plus will be smaller than the magnesium 2 plus. We know that the charge is increasing, the size will decrease. So these two are set. Now what about the lithium plus? Since it is having very few shells, only one shell is there. Therefore, it will have the lowest ionic radius. So it will be smaller than the magnesium 2 plus also and aluminium 3 plus also. If I ask you what is the number of shell in magnesium 2 plus and aluminium 3 plus, what will be your answer? Just think about it. Now moving on to the potassium plus, it has more number of shells than the magnesium 2 plus. So since it is greater than magnesium 2 plus, therefore it will be greatest of all. Now we can write the final order of the given species. So lithium plus is the smallest one, then your aluminium 3 plus, magnesium 2 plus, and lastly your potassium plus. So the first element is larger because of the greater number of shells. The last element is smaller because of the smaller number of shells. In between these two, we have the isoelectronic species which are acting according to their nuclear charge. Okay. So what you have to do, you have to arrange them in the ionic radius, increasing order of ionic radius. I hope this is clear to all of you. Moving on to the next question. You have to compare quantitatively the first ionization potential and the second ionization potential, which are represented by IP1 and IP2 of copper and zinc. So you have to simply say that which one will be greater for both copper and zinc. Either the ionization potential 1 will be greater for copper or zinc. Similarly, your second ionization potential will be greater for copper or zinc. You have to compare that. And then you have to think about the possibility that why it is so. So this was asked in 1996. Your time to solve this question starts now. So just think about the noble gas configuration, okay? That which one will attend the noble gas configuration about after the removal of electron. Okay, your time is up. So if you know the answer, you can just write it here. For those who have solved it, So zinc will have a greater ionization potential. The first ionization potential of zinc will be greater than that of copper. But the second ionization potential of copper will be greater than zinc. Let us try to understand with the help of the electronic configuration. So first we will consider the first ionization potential, which is represented by IP1. So when we are moving from copper to copper plus, what is happening? We are removing one electron from the 4s. Now that results in a stable configuration, which is D10. Okay. So what we can say, that since your electron is removed from 4s1 and it is resulting in a stable 3D10 configuration, therefore this process will occur more efficiently as compared to the other process. So let us try to compare it with the zinc now. Think about the zinc configuration. It is 4s2 3D10. As soon as you remove the electron, you are not moving to a stable configuration as compared to the 3D10. Okay, you don't have a stable configuration like the 3D10. So since you are doing it so, therefore it is relatively less stable. Okay, your zinc removal of electron is relatively less stable than a copper, and hence it is requiring more amount of energy. So we can conclude that the ionization potential 1 of zinc is greater than the ionization potential of copper. First ionization potential of copper. Now moving on to the second ionization potential. What we can say about the second ionization potential? So your second ionization potential will move in this way. Copper plus will move to the copper 2 plus, where you will remove one electron from the stable 3D10 configuration. So what we can say, that we are removing electron from the 3D10 configuration. Therefore, it is difficult to do so. But if we consider the zinc plus, we are removing an electron from the 4s1. And when we do it so, it results in a stable 3D10, right? So you can easily say that the second conversion, which is zinc plus to zinc 2 plus, is very easy as compared to the copper plus to copper 2 plus, because in the second case, we are moving on to a stable D10 configuration, which is a fulfilled orbital, fulfilled subshell. So finally, we can write that the second ionization potential of copper is greater than the second ionization potential of zinc. Then here is our next question. Arrange the following as stated. You have to arrange them in the increasing order of ionic size. So the species are given as N3 minus, Na plus, F minus, O2 minus, and Mg2 plus. Your time to solve this question starts now. Okay, your time is up. So what will be the correct order for this? The smallest one will be Mg2 plus, then the sodium plus, F minus, O2 minus, and N3 minus. Okay. Why we are saying it so? So we have already seen this thing multiple times, that for isoelectronic species, the ionic radius is inversely proportional to the integral value of charge. So we can write here, what is the order of nuclear charge? So Mg2 plus is having the greatest charge. Then comes your sodium plus, F minus, O2 minus, and N3 minus. And as they are inversely proportional, we can write it in this way, where your Mg2 plus is the smallest one because of the highest charge on it, as it is experiencing the greatest effective nuclear charge as compared to all of this. So we've already talked about the effective nuclear charge. So that is the reason we are seeing this trend between the ionic radius and the integral value of charge. Now moving on to the next question. You have to explain this following. Now you can answer this question in few words for now. The first ionization energy of carbon atom is greater than that of boron atom. Just try to analyze this question with the help of electronic configuration. The second condition is given that the reverse is true for the second ionization energy. So this was again asked in 1989. Your time to solve this question starts now. So your time is up. What will be the correct statement here? So it is written already. You have to just explain this statement. So what we can write about the carbon and boron? We know a general trend. Now they both are falling in the same period. Therefore, ionization energy increases across a period. We know it. And that is happening due to increasing effective nuclear charge. So first of all, we will consider it for the first ionization enthalpy. Here it is represented by I1. What we can write? The boron configuration is 1s2, 2s2, 2p1. And we have to remove one electron from the 2p. What about the carbon? It is 1s2, 2s2, 2p2. Again, we have to remove a 2p electron. Therefore, you can say up with the general trend that your ionization energy, first ionization energy of carbon will be greater than that of boron. The reason behind it is that because your carbon has a greater effective nuclear charge. We know it that your carbon comes after boron in the same period. Now, the increased effective nuclear charge in carbon pull its valence electron very strongly. And why it is happening? Because they are having a greater number of proton. Your carbon is having a greater number of proton as compared to the boron. I guess you know that why that first ionization enthalpy of boron is less than that of carbon because of effective nuclear charge. So this is the general trend we know. Now what about the second ionization energy? Let us talk about that. So you can see here that our electronic configuration has nothing to do now. Because on removal of one electron, it will result in 2s2 and this will result in 2s2 2p1. Now do not make the mistake of thinking that since your removal of electron from the 2p is resulting in a 2s2, that is full filled configuration, it is stable. Now why I am saying it? Why your 2s2 is not stable? Any guesses? Why I am saying that your 2s2 will be not that much stable although it is full filled? Remember we said that this funda of full filled and half filled is only applicable to P and D or the further higher subshells. It is not applicable to S. Okay? It is not applicable to S because S has no exchange energy. I guess this is clear to you. So no, it is not according to the penetrating effect. It is simply of the reason because the carbon has a greater effective nuclear charge. You know it? When you move from left to right, the ionization potential increases due to the greater effective nuclear charge. Now let us talk about the second ionization enthalpy. It is written here that the reverse is true for the second ionization enthalpy. Why are we saying that? So to understand this, we have to again look at the electronic configuration. When you remove an electron from the 2s for boron plus, you are moving on to the B2 plus. Now removing an electron from the 2s orbital is being followed here for the boron plus second ionization enthalpy. And for the carbon plus, you have to remove an electron from the 2p. Okay, so two cases are here. In the first one, you have to remove an electron from the 2s. In the second case, you have to remove it from the 2p. Again, do not apply the rule of fulfilled here. What is the reason behind the extra amount of energy that you have to supply for removal of electron from the s subshell? as compared to the p subshell. We have talked about this because your s subshell is more closer to the nucleus. Therefore, the ionization energy, the second ionization energy of boron is greater than the second ionization energy of carbon. Very good. So we can explain it in terms of penetrating effect, as you have said, that your s orbital is, or the s subshell is much more closer to the nucleus, or you can say in other way that it is more penetrated toward the nucleus, so it is difficult to remove it from the s subshell, which is the case of boron plus and not the carbon plus. Right? I hope this is clear to all of you. Now moving on to the next question. Arrange the following in the order of their increasing size. This was asked in 1986 and again is a subjective answer type question. 4 species are given here: chlorine minus, sulfur 2 minus, calcium 2 plus, and argon. Your time to solve this question starts now. So, what is common between all these species? How do we compare their size? What is common between all these species? So, they are isoelectronic species, right? They are isoelectronic species. Now, let us try to compare them. So, the correct order will be this. I have said it earlier. Greater is the charge, smaller is the size, lesser is the charge, greater is the size. So, inverse relation is always followed here. Therefore, your S2 minus will have the greatest radius. Then, what we can write here? Again, the same funda. Ionic radius is inversely proportional for the isoelectronic species to the integral value of charge. So, what is the order of nuclear charge? Calcium 2 plus is having the highest charge. Then your argon, then chlorine minus and S2 minus. Okay. So, this will be the order. Right. I guess it is clear to all of you that why this order is coming, because the charge is more on the calcium 2 plus and hence the effective nuclear force is high. Okay. So why are we not considering the van der Waals radius here? This is also very important. So when we are trying to calculate the ionic radius or the radius, we will look at the actual size, right? We will look at the actual size. You can't compare the ionic radius with the van der Waals radius, right? Because for van der Waals radius, first of all, you have to know more about it, that it is between two different non-bonded species, the distance between two non-bonded species and the closest distance. So you can't compare that radius with this radius. Here you have to take the actual value which is possible. Okay, just think from the logic point of view. Do not think it in a way that, okay, you have to find it experimentally. Okay, the actual point of view will clearly say you that, okay, the argon will have the radius greater than calcium 2 plus and smaller than the rest of the negative element. I hope this is clear to all of you. Moving on to the next question. Arrange the following in their first increasing first ionization energy. Now this one is a good one to solve. Magnesium, aluminium, silicon and sodium. So this was again asked in 1985. You have to arrange them in the first ionization energy order. So what you will do, first you will see their specific location in the periodic table, whether they fall in the same group or period or not. If they are not falling it, what is the distance between the period and group, and all of those criteria. So your time to solve this question starts now, and also think about the electronic configuration. So that is the most important part. So your time is up. Let us try to understand this. Okay, we will try to understand it step by step. Meanwhile, I'm telling you the answer. So sodium will have the lowest ionization potential. Then comes your aluminium, then your magnesium, and lastly your silicon. So first we will try to compare the sodium aluminium. Okay, so this is the sequence, we know it. So the reason for the first sequence, which is sodium and aluminium, we can say that the sodium is having a 3s1 configuration. Okay, so it is easy to remove an electron from the sodium as compared to the magnesium. Now the question arises, why we are comparing these two first? Because according to the general trend, the magnesium will have a higher ionization potential. Okay, so this is the general trend. Why I'm saying it? Because as you move from left to right in a period, the ionization potential increases. So magnesium will have a greater ionization potential ideally. But your sodium is getting a noble gas configuration after removal of one electron, and as a result, your sodium will have a lesser ionization potential than the magnesium. So due to higher nuclear charge, the first reason, and the second important reason is attainment of the noble gas configuration in sodium. It is having a lower ionization potential. Now what about the second term? We will compare the magnesium and aluminium. So magnesium and aluminium, if you see, they are having outer cell configuration as 3p1 and 3s2. So you know it that the p electron are less penetrated than the s electron. Therefore, it is having a greater energy. Okay, the magnesium will require a greater energy to remove the electron as compared to the aluminium, where the electron is present in the p subshell. What about aluminium and silicon? So silicon, in silicon you have to remove it from the 3p2, and aluminium you have to remove it from the 3p1. Here we don't have an exception. Simply your effective nuclear charge in case of silicon is more. Therefore, silicon will have a greater ionization potential as compared to the aluminium. So I guess it is clear to all of you why the order is coming so. Part of the PYQs. Now we will see some DPP. Okay. So we'll do a DPP on structure of atom. So this is from the quantum mechanical of model of atom. Here is your first question. Which quantum number determines the shape of an atomic orbital? So why does silicon has a greater highest ionization energy? So there is a question. So let us try to address this first, before moving on to the DPP. Because as you move from left to right, your ionization potential increases. So it is according to the general trend. Okay, right? So this is according to the general trend. We have seen it that as you move from left to right, the ionization potential increases because the size of the atom is decreasing. You have to apply more energy to remove the electron from the outermost shell. Okay, is it clear? Yeah. So moving on to the first question, which quantum number determines the shape of an atomic orbital? So we know it very well that principal quantum number tells us about the energy level. So it tells us about the energy, and what else is described by the principal quantum number. So there is one more very important point. So energy, and the second thing is, anyone who can say the answer? So I'm talking about the dimension. Okay, so dimension and energy. So this will also tell about the size. So if you compare the size of 3p, then 4p, 5p, then 5p will be greater in size than your 4p, than your 3p. So I'm talking about the specific subshells. So it is very important. This obviously tells us about the shape. Now what about the magnetic quantum number? What is the value of this magnetic quantum number? Any guesses? Yes, it tells us about the orientation. How does it tell about the orientation? So there can be three orientation for P subshell. Suppose it is Px, Py, and Pz. So these are described by three unique magnetic quantum number, which is -1, 0, and +1. Px, Py, and Pz. Yes. So last one is the spin quantum number. Why it is used? What is the physical significance of the spin quantum number? It tells us about the spin and which type of spin. That is important to notice here. It is intrinsic. So the electron is not actually rotating. There is no classical analog of this. It is an intrinsic spin. So there can be off spin and down spin. Moving on to the next question. So the correct answer will be B here. For a principal quantum number n is equals to 3, how many subshells are possible? So what are the subshells that is related to 3? It's very easy to calculate the number of subshells. It is n minus 1. 0 to n minus 1. Or you can simply say that the number of subshells is equal to the principal quantum number, which is n. So 3 will be the obvious answer, and they will be S, P, and D. Yes, the correct answer will be 3, which is S, P, and D. Then moving on to the next question. Which of the following has the highest energy in the multi-electron system? See, it is clearly mentioned that you have to consider for the multi-electron system. So what will be the order? And I will say to arrange all of this in the increasing order. So its n plus L value will be 4. I'm writing it directly. So n here is 4, and for S, L value is 0. For 3D, it is 3 plus 2, 5. For the 4P, it is 4 plus 1, 5. And for the 5S, it is 5 plus 0, again 5. So all of these three has the same value of n. But the n value of this last subshell is the highest, which is 5. Therefore, it will have the highest energy. So option D is the correct one. Then moving on to the next question. The maximum number of electrons that can occupy a 3D subshell is. So a very simple formula to calculate it. What is the formula? If I ask you what is the formula to calculate the number of electrons in a given subshell, then what you will tell? So there are questions asked in this way also, that you have to give the formula. Okay, it is easy to say that D subshell has 10 electrons, but what is the formula for calculating the electrons? It is not 12 plus 1. So 12 plus 1 is used to calculate the number of orbitals. Okay, so this is used to calculate the number of orbitals. See, if you put the value of L here, what you will get? 2 into 2 plus 1. So 5. So you know 5 is not the answer. No, 2n square is also not the answer. So 2n square is related to the n term. You have to calculate the number of electrons in terms of L. 4L plus 2, not 1, 4L plus 2. So it's very simple. If you know this formula, then you know the number of orbitals, and the number of electrons is twice the number of orbitals. So 2 into 12 plus 1, that will give you 4L plus 2. Now here is one more question for you, that what is the number of electrons for one orbital? So number of electrons for one orbital. Yes, it will be always 2. So this is very important to remember. So students often make mistake in this question, which is about calculating the number of electrons in the orbitals. It is not the subshell, it is your orbital. So here 10 will be your answer. Moving on to the next question. Which principle states that no two electron in an atom can have the same set of 4 quantum numbers? It's very easy to say. Your correct answer will be Pauli exclusion principle. But what about the other principles? So the above principle tells that the lowest energy will be filled first. Lowest energy will be filled first. And how is the energy decided? With the help of N plus L formula. Then what about the Hund's rule? This Hund's rule tells that you should have the maximum multiplicity. And this maximum multiplicity allows us to first of all fill all the orbitals singly, and then we will pair it. So suppose you have four electrons for the p subshell, you will not fill them in this way. Okay, so this is totally wrong. How you will fill it? First you will fill it singly, 1, 2, 3, and then you will pair it up. So this is according to the Hund's rule of maximum multiplicity, and this is not applicable to the S. So I will tell you about that also. So just take the example of P, D, and S, and all of them suppose are half filled. If I ask you how many exchanges are possible, for the D subshell? How many exchanges are possible for the D subshell? Anyone? So you must have seen this kind of diagram in the NCERT. It goes like this. So from there your answer comes. So what are the number of exchanges your electron can do? So this electron can go here. Okay. It can go here. It can go here. And lastly, it can go here. So for this electron, 4 exchanges are possible. Exchange will be always occurring with that electron which is in the same subshell first, and second, the both of electrons should have the same spin. They have the up spin and they are present in the same subshell. Therefore, these two can exchange their positions. Here your single electron can do only 2 exchanges. So although it is having a greater stability due to its half filled, but it is less stable as compared to the D subshell in the same principal quantum number. But if you consider the case of S subshell, there is no exchange possible here. You can see it. It cannot go to any of the neighboring orbitals because only one orbital is possible for the S subshell. So your time is ended for this test. I hope you got the answer. That your correct answer will be Pauli exclusion principle. Okay. So lastly, your Heisenberg. So it tells us that you cannot determine the position and momentum both at the same time simultaneously for a given electron. So this was all for today's class. I hope you enjoyed the lecture.